So cluster algebras are, on the one hand, combinatorially accessible, and on the other hand, interesting. Reddening sequences are an important ingredient in the combinatorial computational toolbox of cluster algebras. Surprisingly, it's not known, up to my knowledge, how to determine whether a given cluster algebra possesses a reddening sequence or not. Today, I want to recall some classes for which it's known that reddening sequences exist and add a new class to this list. And this is joint work with Gleb Koshovoy and Bernard Keller. So now somehow my OneNote froze. That's weird. Okay, I'm back. Okay. So cluster algebra. A is associated to a quiver Q, where Q is a finite quiver, so finite directed graph. And we don't allow two cycles or loops. And let's say we have n vertices. So this is due to a Fomin-Selivinski. The cluster algebra lives inside the field of rational functions in n independent variables called cluster variables. So we have one cluster variable for each vertex in our quiver. More precisely, the cluster algebra is generated by a recursive procedure. So first we define the initial cluster variables, A1 to AN are corresponding to our vertices as generators. And then there's a recursive procedure called mutation. We can mutate at each vertex of the quiver to obtain a new quiver, a mutated quiver, and a new set of cluster variables. And so this procedure we can repeat. So we get a potentially infinite list of generators. And this procedure is called mutation at a vertex K of our quiver. So it takes the quiver and the set of cluster variables and produces a mutated quiver and a mutated set of cluster variables. An important fact is that this cluster algebra actually lives inside the ring of Laurent polynomials in the initial cluster variables. So this is called the Laurent phenomenon. Due to Fomin-Selivinski. Now, more precisely, there is a specific receipt how to compute the mutated quiver and the mutated cluster variables. Something like that. Somehow my zoom bar is in a certain position. Anyway. So the receipt is written here, and I will just display it on an example. So let's consider the following quiver of 4 vertices and 4 cluster variables. And let's say from the first vertex, there's an arrow to the third vertex. Third vertex has outgoing arrows to the second and the fourth vertex. And there's an additional arrow from the fourth to the first vertex. And now we want to mutate, say, at the vertex number 3. So how do we do it? We follow our recipe. So we leave all cluster variables the same, but we replace the k, in this case, the third cluster variable, by 1 over the old cluster variables times the sum of the product over all ingoing arrows variables and the product over all outgoing variables. So with A1 and A3 prime, so that's ingoing, there's only the arrow from A1 to A3. And outgoing, there's from A3 to A4 and A2. So we have A1 plus A2 times A4 divided by A3. Now we have to mutate the quiver. So for this, we add transits to K. By this, I mean we have an arrow from the first vertex to the third and outgoing arrows to 2 and 4. So we get transits from 1 via 3 to 2 and from 1 via 3 to 4. Then we need to reverse all the arrows at K. So K is 3. And finally, we need to delete 2 cycles. So we delete our 2 cycle here. And this is the mutated quiver with the mutated cluster variables. So the easiest non-trivial cluster algebra is given by the quiver with 2 vertices and 1 arrow, and let's denote the cluster variables by A, B. And then if one computes the corresponding cluster algebra, one obtains that it is the ring generated by A, B, 1 plus E, B over A, 1 plus A plus B over AB, and 1 plus A over B. And indeed, we see here that these are all Laurent polynomials. So if you so this is obtained by recursively doing this mutation procedure, and a priori it might be infinite, but in this case there's a finite list. So if you get bored during the talk, you might recover this. However, in general, this is a very specific case, which is not surprising considering that this was the simplest non-trivial cluster algebra. In general, the cluster algebra is not finitely generated. There is, however, a more relaxed notion of finiteness. Due to Keller, based on the work of Gayotto, Moore, and Knightsco on the physics side, which relies on the notion of reddening sequences. And the way I will state it here, this also involves work of, so to obtain this formulation, Dirksen, Weimann, and Selivinsky, and Cousteau, Dupont, Perrotin. So this relies on the term of reddening sequences. So a reddening sequence is a specific sequence of mutations. It's denoted by S. So it's a, let's say it's a specific sequence of vertices on which we want to mutate, K1 to Kn. So with the property that the mutation along the sequence of vertices of the so-called principal extension of Q is uniquely isomorphic to the co-principal extension of Q. So here the principal extension is given as follows. We add one vertex for each vertex of Q and an arrow pointing from the copied vertex to the copy of the vertex. So if we take our favorite cluster algebra A2, then the principal extension is obtained by adding one vertex for each of the existing vertices and an arrow pointing that in that direction. And now you can guess what the co-principal extension might be. We just add arrows from the copies to the existing vertices. And our reddening sequence is a sequence of mutations in Q. So the vertices I add, they are frozen, and I'm not allowed to mutate at them. But I want to mutate in vertices of Q to transform up to our isomorphism this principal extension to the co-principal extension. So let's make an example. When did I start?
Start at
45 or something?
45, yes. So you have yes, I think like half hour because just plus 5 minutes. Yeah.
Okay. So we take the principal extension of the A2 quiver, and there are two vertices, so we might mutate at either of them. And mutation twice is the identity, so it's fairly simple here to write all options we have. So if we mutate at the second vertex, what we obtain following our mutation procedure is that just this vertex to the second frozen vertex turns around. And now if you mutate at the first vertex, we see that we already obtained a reddening sequence. However, we might as well do the opposite and mutate at the first vertex to obtain, but now we obtain a transit from the second vertex to the first frozen. So it's a bit more complicated. And the only option we have left is here mutating at the second vertex to obtain this is all following this procedure, and now we have to mutate at the first vertex again. And then indeed we obtain the co-principal extension, however, here with a twist. So the first sequence we noted is 2, 1, that's a reddening sequence, and the associated automorphism is the identity on Q. And the bijection on Q is the identity, and real automorphism. So the existence of reddening sequences has nice consequences for the cluster algebra. So first I want to mention that the Jacobian algebra is finite dimensional. So it is some sort of finiteness condition. So the Jacobian algebra of Q with respect to a non-degenerate or generic potential is finite dimensional. So take a completed path algebra and factor out the ideal generated by cyclic derivatives of the potential, where we have one cyclic derivative for each arrow. So potential is a sum of cyclic paths. And the cyclic derivative sends a cycle of arrows A1 to AD to the sum I obtain when I consecutively leave out the arrows which are A. And this is due to Puste-Dupont Perrotin. So let's give a quick example. If Q is the arrows A, B, C, then the Jacobian algebra with respect to generic potential is generated by ABC, but you will see that the composition of any two arrows has to be zero, because if I derive, for example, the cycle, the ABC is the potential. If I derive it for C, I obtain that AB has to be in my ideal, and likewise. So another nice consequence of the existence of reddening sequences is that under my technical assumptions, the von Goncharov conjecture holds. For the cluster algebra AQ. So that means AQ has a nice basis of theta functions parametrized by the tropical points of the mirror dual cluster algebra. So this is the lattice set to n, where n is the number of vertices. And this is due to cross-hacking Kehl-Kontsevich. So last thing I want to mention here is that reddening sequences can be used to compute so-called Donaldson-Thomas invariants. And they can be computed as a product over quantum Bell algorithms. And this is due to Keller and Gayotto, Moore, Neitzke. So now, if you have two different reddening sequences, then there are two ways to compute these invariants. So we obtain a quantum Bell algorithm identities. So, for example, for A2, I think this is due to Reinecke. We obtain the following identity. So if you want to swap x with y, we get this additional factor, and ex here is given by 1 plus q squared q over 1 minus q, and so on. And this all takes place in the non-commutative algebra where x times q is q to the minus, so it's commutative up to some q power, q to the minus 1/2 xy, or q to the minus 1 y times x. Now here are some questions which I have. About reddening sequences. So first of all, as I mentioned in the beginning, of course we want to know which quiver Q admit reddening sequences. Or specifically, is there an algorithm which, after a time which can be bound, spits out a reddening sequence, or that there doesn't exist one? In fact, I coded an algorithm for this in Sage. It has 3 shortcomings, though. 1, it's conjectural. 2, it's super slow. And 3, it's probably wrong. I mean, it probably doesn't always work. So it's just a temporary fix. But sometimes it's convenient if one just quickly needs a reddening sequence for a small cluster algebra. To use an example. And so also, I want to know what's the relation to injective modules and crystals. So we can attach some kind of crystal action to the principal extension, and what's the meaning of this? By injective modules, I mean the following. Let's look at the principal extension of A2. Then we have the second injective module is trivial, and the first one is here the large one. But if we apply a reddening sequence, then the injective modules here, they are trivialized. So if we have a reddening sequence, it seems we can compute the injective modules. But we don't know how to compute a reddening sequence in general. But the other question is also, let's assume I somehow know how to compute injective modules. Then can I produce from this a reddening sequence? I would like to know the answer to that question. And also how to compute injective modules in general.
Injective modules over what? What did you say? Injective.
Come again?
Over injective modules over what? Jacobian algebra, or you didn't say? Injective modules. Yeah.
Jacobian algebra with respect to generic potential.
Okay.
So how to compute the injective modules? As I say, one way would be to compute reddening sequences, but I suspect that's a bit harder. So I suspect it's more the other way around. But maybe also it's possible to compute it with QPA package of gap. I don't know. And also the question is there some kind of tropical algorithm to compute it? Because it's like it's a specific situation here.
Excuse me, I have a question. Does in this case we have derived Jacobian algebra, like Ginzburg algebra coincides with Jacobian, so homology degree 0?
Sorry, come again?
Is it in the case when exists reddening sequence, derived Jacobian algebra defined by Ginzburg coincides with Jacobian algebra itself? So there's no negative homology. Because Ginzburg defined three Calabi algebra whose degree 0 homology is Jacobian algebra. And it's kind of right derived invariant object.
Yeah, I don't know. I'm sorry. So this is also related to another talk later by Béat de la Porte. Where the relation of injective modules and F polynomials are being discussed. So that's closely related to this circle of questions. And finally, another question I have is we have seen, like, if there exists a reddening sequence, then the Jacobian algebra generically is finite dimensional. How about the opposite? Or maybe there's a counterexample, then it would be nice to see that. So I said I state some or recall some quivers which have reddening sequences. So one is the class P, which contains the trivial quiver and is closed under mutation. And finally is closed under extensions. So by this I mean, if you have two quivers in P, then any quiver cooked up by just orienting arrows from one to the other is in P. So to illustrate that, for example, this is our quiver Q, and this is P. then we are allowed to put any errors from Q to P. Any kind of multiplicities we want, but not in the other direction. The other class which is known to exist, the reddening sequence, is the Banff class, which is closely related. They consist of acyclic quiver, are closed under mutations, and under something called the covering.
Excuse me again. For class P, there was also extension by Cephalot Kani. You can add subquivers. Another operation adding subquivers. I don't know whether it works with reddening sequences, but at least.
Yes.
What do you mean by adding subquivers?
Yeah, just consider any collection of vertices and restrict only edges between these vertices.
Right. Yeah. Thank you. I'll just write this down on the next page. Thank you. So the Banff class is also closed under if Q removed one vertex I and Q removed one vertex J is in Banff. And assuming there is no B infinite path through to an arrow from I to J, so I fix an arrow from I to J. Then Q is in Banff. I think it's conjectured that the Banff class is in class P, and both results are due to Bucher-Mashasek. Furthermore, we know that, as just mentioned, that the class of quivers which possess a reddening sequence is closed under, generally is closed under mutations and taking full subquivers. So this is due to Muller. And it's also closed under extensions. So this was the property P3 from class P, and this is due to Kao-Lee. And it's probably, when I wrote this down, it should also be closed under a B3 Banff extensions. If somebody objects, please send me an email. And today I want to add another class, which is taking triangle products with Dünking quivers. So this is due to joint work with Keller and Koshova. And here this symbol denotes the triangle product defined by Keller, which one obtains by partially triangulating the product of two quivers. So by partially, I mean one triangulates the product part. If the original quiver is one triangulated, one leaves that alone, but triangulates whatever one can in the product part. So here's an example. So here you take the red quiver, the D4 quiver, and the blue, the A4 quiver, and then you take the direct product, and the white arrows are the triangles which appear. So here are the key ingredients in the proof of this result. First is the observation that D equivalent D is Dünken, if and only if it has a sinc maximal Green sequence or a sinc maximal reddening sequence. So by this I mean a reddening sequence which only mutates at sincs. Also, we conjecture that if we have two acyclic quiverts which are not Dünken, then the triangle product has no reddening sequence. And secondly, if S is a reddening sequence, so to prove this result, we consider a quiver, a reddening sequence S for some quiver Q, and the sinc of another quiver R. For this, it doesn't necessarily need to be Dünken. And then one shows that the triangle product of QR mutated at S times D is by the automorphism associated to S isomorphic to Q times triangle product RT, where I mutate just R at the same T. And this follows from a generalized mutation rule. I think I have 4 more minutes.
Yes.
Let me just copy this mutation rule. So the generalized mutation rule looks as follows. We consider a quiver R, a full subquiver of a quiver Q with reddening sequence S. And then if B denotes the exchange matrix of the original quiver Q or the mutated quiver Q at the reddening sequence S of the subquiver R, then they have the following relation. The mutated matrix is obtained by the original matrix by, of course, we need to take care of the permutation somehow, but basically conjugating by E, where E is the following matrix. Of course, we know if you mutate a reddening sequence, we have this -1 factor on R, and we don't do anything on Q without R. And then we have here some lower triangular part, which is the dimension vectors of the projective modules of the Jacobian algebra associated to the vertices which we do not mutate. And the proof of this uses work of Yama, Yoshido, and Palu. So maybe I can show an example. To remember the shortcut. Emacs sometimes is annoying. It's Control-C, Control-J to send these things to Sage. So right, I have opened a Sage window, and so let's consider the A2 quiver. And we take the triple triangle product of the A2 quiver itself, which looks as follows. And then this comes with an explicitly given Green sequence. So this result is explicit, and it doesn't really take time to compute. And for example, if we want to compute the dimension vectors of the projective modules of a principal extension, then we obtain this. So we can use it for such kind of thing. But I mean, it's not computationally expensive. So for example, if you want to take the 6 times triangular product, we can do it in the remaining time, I hope. Yeah. So I guess it doesn't really help to plot it, but let's see. Oh. Yeah, I didn't expect that. Okay, I guess it, well, here we go. And the Green sequence is as follows. Okay. Yeah, well, I mean, I have another example prepared where we display the generalized mutation formula, but I'm out of time, so if somebody's interested, then I'm happy to receive emails.
Over here. A couple of minutes for questions.
Maybe you said this and I missed it, but if a cluster algebra has a reddening sequence, is it finitely generated?
No. No, I mean, it's like a relaxed notion of finiteness. I think there are only like finitely many or very few finitely generated cluster algebras. But reddening sequences is quite prominent phenomenon. I mean, maybe it's difficult to say how I mean, probably a random cluster algebra doesn't have a reddening sequence, but a lot of cluster algebras appearing in nature do have reddening sequences.
Okay.
And well, for example, Markov QER has no reddening sequence, but somehow it's not much worse than those who have, because you, in a sense, can have infinitely long reddening sequence. So I don't know if you can include this property. If you can allow infinite sequences.
Yeah, I was actually asking the same question to Bernard Keller the other day. And I mean, yeah, I guess it's not clear what an infinite reddening sequence is, but on the other hand, you have Q dialog identities and their infinite products. And in some sense, reddening sequences correspond to Q dialog identities, well, roughly. So maybe there's a way to make sense out of it. But yeah, I don't know. Maybe if one works with the stability manifold, maybe there's a way, I don't know.
More questions? Think